Just recording. Okay. Cool. Hey, we just did this in calculus earlier today, but we're actually going to use this fact, but in a simpler way today. So much overlap. It's crazy. Not surprising though. Math 120. Change it to blue. Subtle. Okay. So before we get into chapter 4, which I gave you the notes for, we were working on that graphing problem, right? The one that we'll see definitely just like this on the final exam, and we were kind of plugging through those. So what I want to do is I want to bring in from last day. We were working on number 43, which is that first one in the list of problems. And we figured out, okay, well, we've got, we figured out where we're going to have vertical asymptotes, where we're going to have what the behavior is at those vertical asymptotes. We figured out that we have horizontal asymptotes of 1 at y equals 4. And so let's just do a recap of that. From there, we were able to sketch the graph, right? But let's do a little bit of review here. So if we're given some function f of x equals, or actually let's call it p of x, just to try to match a little bit, or I think they even used r, but either way, fine. R for a rational function doesn't really matter, right? But that's when we have p of x over q of x. Then we can start by finding vertical asymptotes when q of x equals 0, right? So we figure out all the values of x that make q of x equal to 0. Okay? Those are the points where we're going to have vertical asymptotes. Okay? So then, from here, right, we need to figure out the behavior of r of x, right? So the behavior of the whole function as we approach these vertical asymptotes, right? Because we could have situations like this, right, where it shoots up to positive infinity, negative infinity, or they could both go to positive infinity, right? And so we need to figure out the behavior of r of x as x goes towards the vertical asymptotes. Oops, vertical asymptotes. Potentially more than one. All right. This is where we can use some sort of table of values, right? In the printout, right, we're looking at the interval and the test point and the results, whether it's positive or negative. We actually broke it down into multiple little test boxes, right, where we let x approach a vertical asymptote from the left and from the right to see what was going on, right? So whichever way you do it, you don't necessarily have to use the table that's in part D of the printout, right? But that's what we're doing, is we're figuring out how r of x behaves as we approach these vertical asymptotes. Then once we know how it behaves around the vertical asymptotes, where these things are, we can move on to the horizontal asymptotes. Horizontal asymptotes. So there's 3 different scenarios, right? And so remember, if we have R of X is P of X over Q of X, if we say that P of X has degree n, meaning the highest power in P of X is n, and Q of X has degree m, confusing because they sound very similar, then if n is less than m, and we've got this on the printout from last day, right? If n is less than m, so you've got a lower degree in the numerator than in the denominator, then we have a horizontal asymptote, which we can abbreviate HA, at y equals 0. If n is equal to m, then we have a horizontal asymptote at a over b, where a is the coefficient of the first term in P of X, and b is the coefficient of the first term, or the leading term in Q of X. Then we have a horizontal asymptote at y equals an over bm, where we'll just clarify, right? P of X is an x to the power of n plus all the way up to, oops, I'll say a0 instead. And Q of X is b sub m, x to the power of m plus all the way up to b sub 0.
So if n equals m, that's the 2 coefficients are the same, or
so
the 2 degrees are the same?
If the 2 degrees are the same, then you have a horizontal asymptote at a over b, the coefficients of the 2.
Okay.
Right. Let's have a look. If you flip to the next page, right, where we've got all those functions that we're working with, right, and we have a look at something like number 44. Right. Just for a quick example here, number 44 says that R of X is 2x plus 6 over negative x, 6x plus 3. Right. So here, n equals 1 and m equals 1, so they're the same. Right. And let's just call this a equals 2 and b equals negative 6. A subscript n if you want, and b subscript m if you want. But if you just want to talk about them as a and b, that's fine, because they're the only ones that we really care about, right? And so what this says is that we have a horizontal, oops. Therefore, we have a horizontal asymptote at y equals 2 over negative 6, or negative 1 over 3. Just simplifying, but if you left it at 2 over negative 6, that's fine. So that's how that's going to work. And then the last situation is if we have a higher power in the numerator and a lower power in the denominator. And so the last one is if n is greater than m, then there's no horizontal asymptote. There is no horizontal asymptote. So it just depends on how these degrees compare to each other. So far we've talked about where are these vertical asymptotes. We need to figure out how things behave around those vertical asymptotes. Then we need to figure out, okay, where are horizontal asymptotes? And usually we need to figure out how things behave around those horizontal asymptotes as well. But once we've got the graph figured out, it kind of falls into place anyways. And so, okay, what's the next thing we need to do? Oh yeah, the X and the Y intercepts. Maybe I should number these. The vertical asymptotes, let's call that thing number 1 to think about. Horizontal asymptotes, number 2, and then number 3, the X intercepts are where R of X equals 0, right? So the values where R of X equals 0. If R of X is equal to P of X over Q of X, the only time that this thing equals 0 is if the numerator is 0, right? Because the denominator can't do anything to make things 0, right? We can't divide by 0, and so the denominator has nothing to do with making it 0. And so here, R of X equals 0 when P of X equals 0. So usually, if we've got a quadratic, for example, in the numerator, then we can use the quadratic formula to figure out where the zeros are. And then that will be your x-intercept of this thing, right, where it crosses the x-axis. The easier intercepts to find are the y-intercepts. Actually, that's where x equals 0. I will say that actually. Where x equals 0, right? So then we just evaluate R of 0, plug in 0 for x and figure out what your y is, and then you've got your y-intercept. I'd say that's the easiest one to kind of get a handle on. One thing that I think I glossed over and completely kind of forgot about, and it shows up on your assignment. Arvinder, do you remember which question? It's from section 3.6, right? So the last one in the quiz for 3.6 uses this little guy, the 3.6 notes. Oops. So here, once you found the x and the y intercepts, you're done. You have all the components that you need in order to graph this thing. And then you can compare it with what you get from Desmos. But one other loophole, right? Let's call this kind of the end of the review from last day. In quiz 3.6, let's call it, and the last question, we need to use the following. I've stolen the common factors in the numerator and the denominator, right? And so all along we've had little notes saying, hey, we're assuming that P of X and Q of X don't have any common factors, right? if we're able to simplify and find common factors, right, then what happens is that we would be able to cancel those, right? But we actually can't have those values of x in the denominator because they would make it 0, right? And so what that translates to in the graph is just a hole in your graph, right? And so far, we have assumed P of x and Q of x have no common factors. However, if, let's say, and you know what, I want to use one kind of like, let's say, what do I want to do? However, if they have common factors, right? Let's say we have r of x is something like x minus 1 times x plus 2 over x minus 1 over x plus 3. Right? What would happen here, and you might have to factor to get here, right, to check that you don't have any common factors. So now we've got these common factors here. A common factor. So when we're looking at finding our vertical asymptotes, for example, right, we would say, okay, well, x minus 1 is 0 when x is 1, right? And x plus 3 is 0 when x is negative 3, right? And so here, usually we would say that x equals 1 and x, I'll just start with usually, we would say x equals 1 and x equals negative 3 are vertical asymptotes, right? Because that's where we have division by 0, and so that's bad news. But because we can cancel out the x minus 1 with the x minus 1, that doesn't disappear. It's still going to be in there, and it's going to be an issue of the graph from the original function, right? But how it behaves is not a vertical asymptote anymore. It's going to just be a hole at x equals 1. Yeah. So since x minus 1 can be canceled with the x minus 1 in the numerator, x equal to 1 is no longer a vertical asymptote, is no longer a vertical asymptote, but will instead be a hole in the graph. So if we had to sketch this thing, right, we can find the vertical asymptotes, but then we're saying, okay, we're going to cancel this. So I have a vertical asymptote at negative 3, at x equals negative 3. If I look at how these powers behave, right, my highest power in the numerator is going to be x squared. Same thing with the denominator, right? If I expand this and simplify it, the power or the coefficients in front of each of these x squareds, if I expand it and simplify, it's just going to be 1 and 1, right? And so what I have right? Therefore, there's a vertical asymptote at x equals -3 and a hole at x equals 1. I find that there's a horizontal asymptote at y equals 1. Because I've got degree 2 over degree 2, and so they're equal to each other. So then I take the coefficient a over the coefficient b, which is 1 over 1. So then I'm at y equals 1. Right? I'm doing this one a little bit quicker just because we're just going to check it against Desmos anyways. Right? So now I've got my horizontal asymptote, I've got a vertical asymptote, I've got a hole at x equals 1. I can find my x-intercept. My x-intercepts are when the numerator is 0, so x minus 1 and x plus 2. X minus 1 times x plus 2 equals 0. That's when x equals 1 and x equals 2. Something I should have looked into, is the x minus 1 affected as an intercept? Might not be an x-intercept anymore. I guess we'll see. But x equals 2 will definitely be an intercept. And then the y-intercept is when we plug in x equals 0 into this thing. So r of 0 is 0 minus 1 times 0 minus 2 over 0 minus 1 times 0 plus 3, which puts me at -1 times -2, so 2 over -3. One thing I haven't done is I haven't looked at the behavior of this thing as I'm approaching this vertical asymptote of -3. Sure, let's do it. The behavior of r of x as x goes to -3, right? The vertical asymptote. So what I need to do, and you can use the table that's given, or sometimes it might be nice to just have it on a number line, right? Because we're only concerned with -3 here. So what I can do is I can figure out how r of x behaves as x approaches -3 from the left, and then as it approaches -3 from the right. So if I pick values of x going to -3, do you remember we used the superscript negative from the left, right? And then from the right, we get r of x. And since I've got room for 3 of these guys, so from -3 from the left, that puts me at things like -3.1, -3.01, -3.001. I'm inching closer to -3 from the left. And then I can kind of break up the space here at -3. So then I'm going to look at how x behaves as it approaches -3 from the right in r of x. So we've got r of x. In the printout that I gave you, right, it says that you could use a sign test. Okay, so what that means is we break it up and we look at this function like this, right? And we just say, okay, well, if I'm approaching -3 from the left, right, I've got a negative minus 1 is negative times a -3 plus 2 is still going to be negative. And so that's going to be negative times a negative, right? I prefer to just do the actual numbers and kind of look at it, how it actually behaves as I approach -3 from the left and from the right. But you're welcome to use the sign test. We've used it before, but it was a while back, right? And so welcome to use it, but here, let's see what happens here. So we've got, I guess I should copy down what r of x is. R of x is x minus 1 times x minus 2 over x minus 1 times x plus 3 negative 3.1 minus 1 times negative 3.1 minus 2 divided by negative 3.1 minus 1. Gonna add another one here, another bracket times negative 3.1 plus 3. You get 51. You can kind of tap out, assuming that the next one is also large and positive or larger and positive, then kind of call it a day. Negative 3.01. Wish I could remember how to store stuff in here. Do you guys know how to store stuff on your calculator? There's always a way, but sometimes it's a little sneaky. I've got a store function here. Store as whole. Anyways, that would be really handy right now. I'll have to look into it on mine. But if you know how to store stuff on your calculator, right, then you can just plug it in. Times negative 3.01 times 3. Phew. I get 501, which kind of makes sense because then hopefully I get 5001 at the next one. Okay, so it tells me that as I'm approaching -3 from the left, right, I'm shooting up in the positive infinity direction, right? And so now we can do the same thing from the right. And so we get negative, oh, not -3, negative 2.9, let's say, negative 2.99 and negative 2.999. Again, once we do one, we can kind of figure out if it's positive or negative, right? And that's where the sign test comes in, because it'll just be able to tell you how it behaves around that number. But negative 2.9 minus 1 times negative 2.9 minus 2 divided by bracket, bracket, negative 2.9 minus 1 times negative 2.9 plus 3, bracket, bracket. So I get negative 49 here. So hopefully, once I keep doing these, I end up at negative 409 and negative 4009 if it follows that same pattern that we've been seeing. I'll do the last one just to confirm. Negative 2.999 minus 1 times negative 2.999 minus 2 divided by negative 2.999 minus 1 times negative 2.999, wait, 99 plus 3. Oh, not 0, 999. That makes more sense. There. Yeah, that makes more sense. Or, right? Or using the sign test, right? If we're looking between or around -3, right? Because that's where we decided we have a vertical asymptote. What we do is we remember that r of x is x minus 1 times x minus 2 over x minus 1 times x plus 3. So then, if we think about values to the left of -3, let's do something simple to think about, like negative, oh, that's not to the left, -4. That's to the left, right? If you just pick a random test point to see how it works in there, right? Then you have -4 minus 1. You don't have to think about what the value is. You can just think about what the sign is, right? And so -4 minus 1 puts you at a negative, times -4 minus 2 is also a negative. Oops. Divided by -4 minus 1 is still a negative. Whoops, not -1, but negative. Times -4 plus 3, negative, right? Which means a negative times a negative is a positive over a positive, making a positive value, which is what we said here. We're going to go towards positive infinity, right? And so it's going to go kind of up this way, right? So here we can do the same thing. We just pick a point that we want to use just because it's easier to think about actual numbers going in there. If we do -2, or let's make it even easier and do 0, right? 0 is to the right of -3. Okay. 0 minus 1 is negative. 0 minus 2 is negative. 0 minus 1 is negative. Oops. Is negative. And 0 plus 3 is positive. Negative times a negative is positive. Divided by a negative, though, gives us that negative that we found earlier, right? And so here means we're going this way. So this is the sign test, right? When we just look at the sign of things. So then we don't have to compute these values, although it definitely works, right? It's kind of, for me, this is kind of where I start, because then I can kind of think about how it behaves. But then once I get a handle on that, then I can say, okay, well, it might just be easier to use the sign test, right? So either way, whichever way you prefer, will work, right? But the key is to figure out the behavior around those vertical asymptotes. Okay, so now we know we've got this type of situation at the vertical asymptote. We've got a horizontal asymptote at 1. So now we can kind of sketch this out here because we know a lot about this thing now. Oops. Let's say here we're at 1. And what was all the information that we had? A vertical asymptote at -3, a hole at x equals 1, and a horizontal asymptote at y equals 1. So here we're at 1, -1, -2, -3. So we decided we have a vertical asymptote at -3 and a horizontal asymptote at 1. And a hole at x equals 1. So we know around the vertical asymptote, we're going to have this type of behavior, right? And they're going to behave the same way around the horizontal asymptote. So here, right, we put that little guy in that corner, going up towards positive infinity. And then down here, right, we have to follow that horizontal asymptote and then curve down towards negative infinity. And so what we have, remembering that we have a hole at x equals 1, but that line is just going to follow this horizontal asymptote until eventually it curves down. Oh, I forgot one thing, didn't I? I forgot one thing. My x and my y intercepts. X equals 1 and x equals 2. And a y-intercept at 2 over... How's that going to work? The y-intercept, x-intercept. We might have to pull in the big guns here. Do you see the problem? 2. Oh, because it's -2. No, -1 times -2 is 2. -1 times 3 is -3. 2 over 3. I wonder if we ignore the x minus 1. Something I should have looked into, shouldn't I have? Shouldn't I have? Let's graph it out and see what happens here. X minus 1 times x minus 2 divided by x minus 1, oops, times x plus 3, I think I did. Oh, I just drew it wonky. We found all our things pretty well. 2, 0, and hey, we should have a hole at x equals 1. But it's not showing, is it? Ha! There it is, but it's not showing up. You have to be right on, and it's impossible to tell, but there is a hole there, which we're going to draw. So instead of drawing my graph willy-nilly, what I should have done, let's do this instead. There, nothing happened. So I should have drawn my x and my y intercepts first, so I could map this thing out. Doesn't help that I'm not really to scale here. Kind of wonky. Okay, what do we have here? All right, Time to do it properly. X equals 1 is not going to be an x-intercept because it does get canceled. But is canceled out. Right. So then we have at x equals 2. Actually, let's use a different color here. At x equals 2, all right.
X equals -2.
Is it? That would be better. Would look a lot nicer, that's for dang sure. It is too. Hey, so what did I do here? Hey, I've been using the wrong. It's x plus 2 over here. But then at some point here, I started using -2 and I messed it all up. Oh no, I'll use red. How much is that gonna change? Changes my, you know what? Because I've been using x minus 2 all throughout, instead of change, I'm gonna change the original. Otherwise we have to change way too much. Okay, sorry guys. I need to be more careful. Change this to -2. Because that's what I've been using. Ugh. Okay, so then x is 2. Hopefully I didn't flip-flop. No, I didn't. Is going to be our x-intercept, and then at 2 over 3, which is 0.66, but negative. So 2 over 3. Okay. Looks like I cross the axis here at x equals 2, and at negative 0.66. Negative point, oh, well, x is 0. And here at 2, 0. And I've got a hole in the graph at this point. Right, so not an asymptote, but a hole here. Okay.
So is the difference between a hole and an asymptote, the line can cross a hole, but not an asymptote? It can't like cross an asymptote and then continue?
Exactly.
Okay.
So it'll never hit an asymptote, and it, just like the hole, but everything just behaves the same way heading into it, right? Because essentially it's kind of canceled out. So you can't be at that value, but you can get close to it and it behaves the same on either end. Right? So we've got a discontinuity there. So, all right, now I can kind of, well, if my graph was kind of more to scale, I guess, I can connect these two and kind of send this guy down, something like that. But just remember that here you've got this hole. I'm okay with the other side. But I think it was my axes and my forgetting to graph my x and my y intercepts on there didn't help. So now we can just make sure that it looks the same on Desmos, which if we zoom out here, we're approaching -3, +3, or sorry, -3 from the left. And like I said, if we zoom in here at x equals 1, let's see, how far do we have to zoom in? It'll never show the whole. There, undefined, doop, which is at x equals 1. Sneaky though if you're just looking at the graph on Desmos, because it doesn't show clearly that there's a hole there. Okay, did it. But that's also the reason why a lot of these definitions are saying, hey, we're assuming that we don't have any common factors, right? Because when we have common factors, that's when we have the holes. Otherwise, things just keep going as per usual. Okay.
Can we do one more example?
Yes, we can. Don't worry, chapter 4 is way more fun. Don't worry. And I'm really bummed that we only get to spend a week in chapter 4, but anyways, let's do another one because these are pretty tricky. Should we do you want to do 60 or 61? I know you guys have solutions to the odds, so, but doesn't matter to me which one.
61 was complicated.
Should we do 61 then? Yeah, because if you can do 61, you can do 60. I mean, they are basically the same. So let's do 61. So we've got r of x, 5x squared plus 5 over x squared plus 4x plus 4. What I'm going to do is I'm going to bring in those questions that we are going to have on the final. I might take that table out. I don't know if you guys want the table in there. I mean, it's not part of the question, so I can do that. Let's see here. If I copy and paste it in here, oops. Come on. Paste it there. You know what? Let's put it in where it's supposed to be here. 5x squared plus 5 over x squared plus 4x plus 4. It's the one that we're doing. Gets its own page. Okay, so part A that we're gonna do is find, well, here it's kind of a giveaway. So on the final, it'll have 2 vertical asymptotes, right? Which tells me that it's probably gonna be some sort of quadratic in the denominator, right? Because that's when I have 2 vertical asymptotes. So good thing that's kind of similar to what we're working on here. So if we go to part A, find the vertical asymptotes, and steal this one more time here. You've got it in front of you, but I don't want to be scrolling up and down all the time. So here, the vertical asymptote is going to be when x squared plus 4x plus 4 equals 0. Which we could, I would probably say, let's just use the quadratic formula, right? Because then you don't have to factor, and it's kind of a quick way to factor, in my opinion, right? As soon as we have a quadratic here, right? Or you can look at this and say, well, what value multiplies to 4 and adds to 4, right? So I'm thinking 2, but let's just use the quadratic formula, because that's not always going to be that easy, right? To kind of look at it and say, oh, I see it, right? And so just so we have all the tools that we need for even tougher problems, we can use the quadratic formula, which says that x is negative b plus minus the square root of b squared minus 4ac over 2a. In our case, our b is 4, so negative 4 plus minus the square root of 4 squared minus 4 times 1 times 4 over 2 times 1. So we get negative 4 minus 16 is 0 over 2. So I get negative 4 plus minus 0 over 2, putting me at negative 2 and negative 2. Okay. So like I said here, not always going to be this easy, right? Especially because if we have a look at find the 2 vertical asymptotes, we only have 1 in this case, right? And so the one that we work with on the final will have 2, right? So we will end up with 2 solutions there, which we usually do with the quadratic formula. Right? But what this says is that we have a value of 0 when x equals negative 2. So if we had to factor this out, right, then we can say that x squared plus 4x plus 4 must be x plus 2. That's right. Because what we get is the square root of 0, right? 16 minus 4 times 4 is 16, so 0. And so that's why we only get 1 value. Usually we get another value there, let's say 1, right? Negative 4 plus 1 divided by 2, negative 4 minus 1 divided by 2. Right? So we can write it as x plus 2 times x plus 2 if we wanted to. The reason I like to split them up like that and not have x plus 2 squared is because when we're using the sign test, for example, which might be a little bit quicker than plugging in values, then it's just easier to look at. Right? And now it's easy to see that when x equals negative 2, well, both of these are going to be 0, and so the denominator is 0. So that's where I have a vertical asymptote. Right? So therefore, we have a vertical asymptote at x equals negative 2. Part B says find all horizontal asymptotes, if any, and clearly state the y values where they occur, if any. Right? So now we're going to look at the horizontal asymptotes, which means we need to figure out what the degree of the numerator is and the degree of the denominator is. In this case, they're both degree 2. The coefficient of the numerator is 5 over 1. Means we have a horizontal asymptote at y equals 5. So part B, find the horizontal asymptote. If we have r of x equals 5x squared plus 5, I'll just copy it from here, x squared plus 4x plus 4. Right, we can just make a note here that the degree here, the highest power is 2, and here we have a degree also equal to 2. Right? So therefore, right, we've got a horizontal asymptote Therefore, we've got a horizontal asymptote at y, at y equals 5/1, which is just y equals 5. So,
How could you have two horizontal asymptotes?
we won't. We'll only have one. It depends if you kind of consider it being split, but we've got a horizontal asymptote at 5, and then, yeah, how would it happen if you had multiples? I guess if you were able to split up into two rational functions, but no, we're just gonna have one. One horizontal asymptote for us. Yeah. Because you would have to have a combination of two rational functions, and so, which can happen, right? But those functions are way too big for us. So don't worry, we'll just have one. So then part C says what? Find the two X intercepts and clearly state the X values where they occur. So in this case, right, we've got two X intercepts. That's not necessarily the case for us, but on the final we'll have two. So we need to find the X intercepts, and that's where R of X equals 0, right? So we're looking for where 5x squared plus 5 over x squared plus 4x plus 4 equals 0. Right? And so this is when, so R of x equals 0 when the numerator is 0, right? So when 5x squared plus 5 equals 0. So 5x squared plus 5 is going to be 0 when, so we can solve, so, and you can absolutely use a quadratic formula here if you wanted to. In fact, maybe just as a go-to, right, you can have a look and you can solve this, right, move the -5 over, divide by 5, then you've got x squared is -1, and then take the square root, which puts you at plus minus square root of 1, right? Pulling out the negative cheating. Pull it out?
Yeah.
Because in the plus minus, we can
okay.
cheat that way. But it's harder to think about, right? And so for me, if I want like a safe way to do all this, I'm going to use the quadratic formula, right? Again. So here we go. Sorry. Keep getting these weird calls, but it buzzes on my arm, so turn it off. Okay, so x equals -b plus minus the square root of b squared minus 4ac over 2a. So we've got -0, right? Because our b is actually 0x, right? -0 plus minus the square root of 0 squared minus 4 times a, which is 5. Hey, what the? Did I copy it down wrong? 5x squared plus 5 -4. I just don't want to take the square root of a negative because I can't. A is 5, C is 5. Let's see how this plays out. I don't see it working, but it should. 0 or true. Here I've gone on and on and on about the safest way to do stuff. That doesn't work. I'll put it over 2 times 5, but here's where I'm kind of screeched to a halt, right, is that we can't divide by a negative. Or sorry, we can't take the square root. We can't take square root of a negative. Exclamation mark. All right, so I guess we'll have to solve it. So we do 5x squared plus 5 equals 0. 5x squared, why didn't it work? I will have to figure that out. -5, we've got x squared is -5 over 5. So then x squared is -1. But I can tell by looking at this thing does this mean there are no x-intercepts? I was thinking is 5x squared minus 5, but I've checked a bunch of times and it's 5x squared plus 5.
So you can't pull a negative off the line.
I don't want to. I was going to, but I don't want to. Because I was going to argue that if you did -1 squared, for example, right, that would just put you at 1, but then you're at 5 plus 5. I was looking at it as 5x squared minus 5, and then it would work, right? But then you also wouldn't have that trouble with the -1 and the square root. So I don't think there is an x-intercept for this one. You picked a hard one indeed. We'll confirm with Desmos, but it looks like there is no. So what I'm going to do here is, because we keep landing on, we can't take the square root of a negative. So I think what we can do is we can just put the brakes on. I'm going to delete this here because we don't really need it. All right. And so what I'm going to say is that therefore there is no x-intercept. There is no value of x that I can think of here that is going to give me 5x squared plus 5 equals 0, because I can't get a negative out of a square without imaginary numbers. So therefore, there is no x-intercept. Obviously, from the question on the final, there will be 2 x-intercepts, because I'm pretty sure that's what it says. Find the 2 x-intercepts. Well, if it's a trick, I'll change it and I'll say, find the non-existent x. No, it'll have an x-intercept. What this tells me, if there's no x-intercept, likely what's happening is you've got something like this and it never crosses the x-axis, right? Or something like this, where with a horizontal asymptote above the x-axis or below the x-axis, right? So already, if this is the case, right, then I can have a good idea of what it's going to look like. Right? Otherwise, it would have to cross the x-axis at some point. But we'll see. Okay, that mess. Did not see that coming. Man, oh man. You guys sure know how to pick them. Okay. Toughest ones. Let's see here. Find the two X intercepts. In part D, we're just figuring out the behavior as we approach the vertical asymptote. So here we thought we were so lucky because we only have one vertical asymptote, but then there's no x-intercept, making it hard again. So part D, find the behavior of R of x at the vertical asymptote. So this is where it gives you this table that you could use if you want to, and I'll show you how we would use it. Or you can just use the way that we have been doing, which I'll show you below, right? But you'll see that it's the same thing, right? So we've got a test point, and we want to work around kind of at -2, right? Well, let me just double check. X equals -2, right? That's where we've got this vertical asymptote, and we have to figure out what's going on here. So here, we're at x equals -2. So if we pick a test point to the left of -2, right, then I can have something like -3. This is for the interval from, oops, does not like me writing on this thing, from -infinity to -3, or sorry, -2 actually, up to the vertical asymptote. And then on the other side, we're going from -2 up to +infinity because there's just the one vertical asymptote. So to the right of -2, I'm going to pick 0 because I always like using 0 whenever I can. And if we use a sign test, then we've got 5x squared plus 5. X squared plus 5 over, did we factor it out? X plus 2 squared. So we've got 5x squared plus 5 over x plus 2 squared. At -3, right, we've got a positive value in the numerator, right, because -3 squared makes a positive times a positive plus a positive makes a positive over -3 plus 2, but then we square it, makes a positive, which means I'm going to +infinity. Same thing here. If I do 5x squared plus 5 over 0 plus 2 squared, or actually 0 plus 2 squared. Plugging in 0, I still get a positive value over a positive value, which gives me an overall positive value. Which confirms what we were thinking, that they would just, if there's no x-intercept, they must be heading towards in the same direction, right, around that vertical asymptote. Or how we've been doing it, right? So if you want to, you can just ignore this table because I actually don't find it very useful. I don't really like mapping it out like this, right? How we've been doing it is we've got a number line here, and at -2, that's our vertical asymptote, right? I pick a test point, I can still use that test point of -3 and 0. And so what I get is I get, and I can use the sign test, right? A positive over a positive is a positive value, and a positive over a positive is a positive value. So at -2, well, really slanted there, what it's going to look like is I've got this type of behavior going up to positive infinity on either side. Right? Or the third option is to plug in actual values and just figure out what the behavior is.
Wouldn't it have to be above the x?
Yeah, I'm using it as a number. I'm not actually using it as, but yeah, it's because I didn't give myself enough room. But actually, you're right. I should do this, something like this. Nice. Okay, so now part E says use a table of values to determine the behavior of f of x as x goes to infinity. So now your answer should include a superscript. I don't know what that means. Jenna, we talked about it. We could not figure out what that might mean. So just ignore that. And I'll even remove it. I'm assuming it has something to do with from the right, from the left. But honestly, because it's not clear to me or Jenna, let's not worry about it. And all it's asking for is the behavior around the horizontal asymptote, but here, right, it's always just kind of gonna flatten out around the horizontal asymptote. So part E, I'm gonna say we can ignore this one, right? I'll cut it from the test because it's not clear to me, and the horizontal asymptotes will always just kind of behave the same way, right? And so assuming we found, oh, we did find all the horizontal asymptotes. Yeah, so we're good. So we can ignore this one or this part. Now, I am going to steal the graph because I obviously am not very good at drawing things to scale. Okay. All right. So I've got this graph and I'm going to learn my lesson. I'll put my, did we find a y-intercept? No. And I wonder, why didn't we? I think we should find the y-intercept. How about we replace part E with that? Find the y-intercept instead, because we'll need it. Right, but the y-intercept is just when x is 0. So r of 0 is 5 times 0 squared plus 5 over 0 squared plus 4 times 0 plus 4, putting me at 5 over 4. Nice. Just because that's easier to graph. Okay. let's put these guys on the map here. So 1.25, let's put that somewhere here. So I'm at x equals 0, 1.25. I know I don't have any X intercepts, right? That's what we landed on. I can map my vertical asymptote is at -2. So here, I've got a vertical asymptote. And where did we put our horizontal asymptote? At 5. Y equals 5. 1, 2, 3, 4, 5. Hopefully this is it. 1, 2, 3, 4, 5. Okay. Horizontal asymptote at y equals 5. Vertical asymptote at x equals -2. Okay. Let's see here. No X intercepts. We know the behavior at the vertical asymptote. How's it going to go through the y-intercept? That's what I want to know. Because what we're saying is it should look something like this. This question. How's it supposed to go through here? Let's see. 5x squared plus 5 divided by x squared plus 4x plus 4. Oh, come on. I'll put a line at y equals 5 just so we can see. Okay, too tricky for us. Because how are we supposed to know the behavior around x equals 0? We're not supposed to. I wouldn't give you anything that doesn't behave like this, right? Because what it looks like is, okay, we've got a horizontal asymptote here, so we have to abide by that, and then it looks like, okay, we cross here, and then we've got this vertical asymptote, and I'll even scoot this closer here.
But why does it cross the horizontal?
It's allowed to cross the horizontal asymptote, but for us, I want you to just think of these round curves, right? Either flipped around, right? And so this is way too hard without Desmos. And so here, right, I want you to think about, okay, all of ours are going to be variations of that, right? Flipped around, kind of mix and matched, right? But we're not going to have weird kind of dips and stuff going on. Can happen, obviously, but for us, no way. So. Well, let's just graph 60 to see if it's any better. I'm not sure. 4x squared divided by x squared minus 2x minus 3. It's no better. Nasty. No thanks. How about, as a rule, go through and graph them in Desmos first. See if it looks reasonable to do on a test. I would never get you to graph something like this, right? Like I said, it'll be kind of the basic, 1 over x situation, right? So 1 over x looks like this, right? It can be flipped around. It can be kind of going the same direction, right? Look for things that look like this. Bad, bad, bad. I wonder how 59 is. We'll never know. Let's move on to funner things. Any questions though about that one? That was very tricky. Right. But we learned some things along the way. Like we don't necessarily have to have an X intercept, right? If we run into troubles, don't do what I did and try to finagle it. Just call it and say, nope, there's no X intercept, right? That's okay. The methods that we use for finding the vertical asymptotes, the horizontal asymptotes, everything stays the same, right? This is just a very tricky case, right? Especially for graphing it. Okay. Oh, let's talk about exponential functions instead. It'll be way better. So, section 4.1 is on exponential functions. And like I said, I wish we were spending way more time in chapter 4 because, well, one, exponential functions and logarithmic functions are really important and kind of basic stuff that we need to have a good handle on. So it'd be nice if we could spend some more time on it. But also it's really fun once you kind of get into it. So here we go. So an exponential function is any function that has the form a to the power of x. So our x is in the exponent. And so we've got 4.1 notes. So we've got an exponential function with base a, right, is going to be a to the power of x. So we're going to notice that x is in the power. Right? So we say that a to the power of x is an exponential function base a. Right? Okay. If we talk about how the graph of a to the power of x behaves, right, then we can have a look at the next box, which says, okay, well, depending on if the base is positive or negative, that's going to determine which direction our exponential function is growing. So usually in finance or whatever, we talk about exponential growth, right? Population growth, right? Things are growing exponentially. And what that's telling us is that things are growing faster and faster and faster and faster, right? And so here is kind of our typical exponential curve, right? One fact is that it's always going to pass through 0, 1, 0, 1, 0, 1. So the y-intercept is always going to be at y equals 1. So that's kind of a cool fact. And if the base is positive, then we're going up, up, up in the positive direction. So imagine here's how much money you have over time, right? Exponential growth looks great, right? Or if we're talking about decay, right, then we've got a negative a, or sorry, not a negative a, an a between 0 and 1, right? So a decimal value for a actually can't be negative. So if we've got a decimal value for a, then we've got this decay, right? So here we've got, oops. That's what growth looks like. And then here, this is what decay looks like. So we use these exponential functions to model growth and decay, right? And so that happens quite a bit.
So anytime there's decay, it will be between 0 and 1, and that's it.
That's right, yeah. So then the base is going to be less than 1. So then we've got this decay. Okay. It's going to look a little bit different depending on what your base is. Right. So we've got this little illustration, which we'll kind of zoom in on here. Right, so depending on what your base is, 1/2, 1/3, 1/5, 1/10, right, it's just going to kind of come closer to the y-axis. It's always going to pass through 0, 1, right, regardless of what the base is. So let's make a note of that. Always passes through 0, 1. Of course, we use our calculator to calculate these things. So let's just do a little bit of practice, even though I'm sure you've used your calculator before, but it's good to just know how our calculator behaves, right? And so if we do, I don't know, let's do 8. 8 seems like a reasonably hard one. Or do you want to go for 10 right away? Why not? So we're going to use our calculator, right, to find g of x equals 4/3 to the power of 3x. So if we want to find g to the negative 1/2, that means just substituting in x equals negative 1/2 in here. So then we get 4/3 to the power of 3 times negative 1/2. Which, if we simplify, 4/3 to the power of negative 3/2. We're just using our calculator, right? And so what you want to make sure is you have your 4/3 in brackets on your calculator, just so it treats it as one thing. And then to the power of, and usually there's like an X and a blank power button or a little caret button, so make sure you can find it on your calculator. And then negative 3/2 also in brackets, just to make sure that it's all in that power. So I've got 4/3 bracket to the power of, and then bracket again, negative 3 divided by 2. So I get roughly, because I have to round at some point, 0.649519058. Cool. Let's just do g of √6, and then I'll kind of assume that you know how to work your calculator with this stuff, but make sure you get it under control. 4/3 times to the power of 3√6 root x. can just leave it as it. You can simplify it if you want to, but I'm just going to leave it as it is because I'm just plugging in my calculator, putting 4/3 in brackets to the power of, and then brackets 3 times the square root of 6, and then step it out and bracket. Good. And I get an approximation here, so I'm going to use roughly equals 8.281489611. If we have a look at the next question, it's a little bit trickier, right? It's kind of like making us think a little bit. So that's why I want to have a look at that one. Copy. Paste. So for each of these, right, we're given whether it's growth or decay, which is going to tell us a little bit about the base, whether it's greater than 1 or between 0 and 1. Right? And so the first thing we can do is just talk about whether it's growth or decay, right? Just to get an idea. For 21, we've got growth, which means that A must be greater than 1. 22, we've also got growth. So again, A must be greater than 1. And then 23 and 24, both of these look like decay, right? And so now we've got decay. So A must be between 0 and 1. And again, we've got decay. So A must be between 0 and 1. Right? Just to have a good idea of what A might be, reasonable values for A. If we look at 21, and we'll only look at a couple of these because this isn't how we're going to solve these things, right? It's just getting an idea of how do we do these. And so for 21, we know A has to be greater than 1. What it's saying is when X equals 2, Y equals 9, in Y equals A to the X. Okay. So if we're trying to find what A is, we know that 9 equals A to the power of 2. So now we have to think, okay, well, what to the power of 2 gives 9? I'm going to go with 3. Right, 3 squared is 9. So therefore, A must be 3. So the function then, so y is 3 to the x in general, right? We know one point on this thing, but the whole curve has the function y equals 3 to the x. Oh, because A has to be greater than 0. Yeah. Otherwise, it flips it on the x-axis, right? So for now, we're just dealing with positive values of A. Nice. But otherwise, absolutely. How about if we did 24? Why not? We're actually, yeah, that's going to be a decay. So if we've got if we know that when X is -3, Y is +8, okay, then in Y equals A to the X, we've got 8 must be A to the -3. So then I've got, but it should be 1/2, right? Because 2 to the power of 3 is 8. And so I know I'm dealing with 2. And I also know because it's decay that A has to be between 0 and 1, right? And so if I think about let A be 1/2, then I have, does 8 equal 1/2 to the -3? This is going to be the same, right? -3 means I can put it in the denominator. And so I'm going to have 1 over 1/2 to the power of 3. Right? I can rewrite it that way. I can bring that power inside. So I get 1 over 1 to the power of 3 over 2 to the power of 3. That's where I'm going to get that 8 that I want, which is going to be 1 over 1 over 8. 1 I can just rewrite as 1 over 1. Then I've got a fraction over a fraction, which I can flip and multiply. So then I get 1 over 1 times 8 over 1. So 8 equals 8. So we were right. Like I said, this isn't how we're going to solve these, right? It's just to get a good grip on what these things look like. So then A must be 1/2. So then, therefore, y equals 1/2 to the power of x in general, right? Oh, decay. So I know I promised to no word problems on the final, but kind of the fun application of exponents and logs is in finance, right? So if you're talking about interest problems, compound interest, which happens all the time, right, then we're going to use these exponents and logs, right, exponential functions. And so throughout each of these sections, I've got little compound interest problems in there, mostly just because they're good for life, right? Knowing how interest rates behave, right? How do we know how to calculate about these things so it's not so foreign to us? And so potentially the only word problems that we'll tackle here. Actually, let's just talk about, you've got the blurb in your notes. I'll just bring in the moneymaker here, which is just the formula. Okay. So how compound interest works is, so you deposit some initial amount, some principal amount, right? Let's say you deposit $10, right? Every year or every month or whatever, however often things are compounding, what happens is the bank calculates how much interest you've earned on your $10, and then it compounds the amount of interest that you've made onto the $10. And then from that point forward, what happens is that you earn interest on the $10 and the interest from before, right? So you keep earning interest on more than $10 as you keep going, right? So for each compounding, the interest that you've earned in that time of the year, right, gets added to your principal amount, and then you're earning interest on the principal and the interest amount that you've earned so far, right? And so that's how it works. And the formula is just the A of t, which is the amount after t years, right, which is usually what we're interested in, is going to be P, which is the principal amount, so the initial investment that you put in, right, are $10 in our case. And then times 1 plus R over N, where R is the interest rate per year as a decimal, okay? And so R must be a decimal N is the number of times interest is compounded per year, right? So some common ones would be monthly, so then N would be 12, right? Annually, N would be 1. Semi-annually, N would be 2, right? And so here are some common ones. N equals 1 is annually. N equals 2 is semi-annually. N equals 12 is monthly. I think they don't use anything kind of fancier than that. If they do, you can just figure out, you know, if it's weekly, it's 52. Sure. N equals 52 is weekly. And usually we assume that we have 365 days in a year. So daily. But I suspect that for these problems that I've given you, I think you only need to go to monthly and just kind of go from there. Monthly, there. So N is the number of times interest is compounding. And then T is, of course, the number of years, right? Everything's in terms of years. And so let's do a problem. Which one of these should we do? 58, you got it. So we need to map all the information that we're given to the formula that we have, right? So if $2,500 is invested at an interest rate of 2.5% per year, right? Remember, you have to convert that to a decimal. So you have to divide it by 100. Compounded daily, oops, I was wrong. But that's 365, right? N is 365. Find the value of the investment after the given number of years. And so here, let's just map out what we've been given. We've been given that P is 2,500. I'm not going to put the dollar sign on there until the end probably, right? Otherwise it gets a little messy. Our interest rate R is 2.5 divided by 100, which is 0.025. Right? That's the value that we have to use in our calculations. We're given that it's compounding daily, which means N is 365. And for each part, we've got a different T, right? T equals 2, T equals 3, T equals 6. So for part A, T equals 2. So if we use this formula, the amount after time T in general is going to be P times 1 plus R over N to the power of N times T. So we've got a principal amount of 2,500. So the amount after 2 years, A of 2, 2,500 times 1 plus the rate, which was 0.025, over 365. So it's going to give us a really small number. To the power of 365 times 2 years. So BEDMAS, right, says that we have to work inside the brackets. And inside the brackets, again, we have to follow BEDMAS. So we have to do 0.025 divided by 365. 0.025 divided by 365. And then I can add that to 1. So what I get here is 2,500 2,500, and you want to keep all your decimal places, right? Even if you write them down, right? You want to keep all your decimal places in your calculator, as many as you can. So this is times 1.0, 1, 2, 3, 4 zeros, 1, 2, 3, 4, 6, 8, 4, 9, 3 to the power of 365 times 2, 365 times 2, thank you, 730. I lost my other one, so I'm actually just recalculating it so I can raise it to the power of 730, because now I've dealt with the brackets, right? I've just got one value. I have to raise that to the power of 730 and then multiply it by 2,500. So what I get is I get 2,500 times this to the power of 730. 1.0512699296. And it's so important that you don't do any rounding here, because we are talking about money, right? And so especially if you're working with someone else's money, they don't like it when you're rounding too fast, right? You want to keep all your decimal places. So, and then we can multiply by 2,500 to land on 2,628.173241. Because this is money, I know I have to round to 2 decimal places, right? And so in terms of dollars, I've got 2,628.17 after 2 years.
It wouldn't let me just do it.
Oh.
It said overflow. It's weird.
That's weird. It should be able to handle it. It's not that big. Can have a look. But I'm out of time, and I know it. I can see it in your eyes. You're done. So have a look through the rest of the chapter 1 notes, because we didn't really get as far as I was kind of planning on. But what you'll see is that things are pretty reasonable in there. So see you guys on Friday. Way more reasonable than graphing. Let's have a look at that calculator.
I realized what I did.
Oh. Then I don't need to see it.